And so I would like to introduce our very first speaker, Connor Vaught. He is an optical engineer working with AV on directed energy, which is actually where I'm in now, and target tracking programs. He graduated with distinction from the University of Maryland with a Bachelor of Science in Physics and Astronomy, where he was highly involved in high-energy astrophysics research. He works on product development and manufacturing, including free space optical design, optical modeling, optical alignment, anything optical, he probably does it. And when he's not working optical, Connor enjoys rock climbing, hiking, and traveling. So please, let's welcome to stage Connor Vaught.
Hi, everyone. Thanks for the introduction. I'm going to be talking about my job today, which is something that I do a lot, but this time I get to maybe teach some people about optics and astronomy and the things I've been interested in for a very long time. So I am an engineer, but my background is in astronomy. I probably got interested in astronomy when I was a kid. I don't remember, but this is very exciting for me. So my background here is one of my favorite photos from James Webb, which launched a few years back. It's the Carina Nebula in IR, so I thought it was a fitting picture for this talk, but let's move on. So to understand what IR optics are and what IR optics and astronomy entails, you first have to understand optics, which I've found in my last 4 years, not a lot of people know a lot about optics, even though it's our main sense. We use our eyes for everything. And glasses, cameras, everyone has a camera in their pocket, which is, as an optical engineer, pretty cool to me. But so what is optics? Simply, it's the study of light. Optical engineering is then the manipulation of light and designing systems of lenses, mirrors, sensors, diffraction gradients, what have you, to achieve some certain purpose or an imaging spec, something like that. Optics usually refers to between the UVC, UV wavelengths, and the long wave IR, which is about 100 nanometers to 15 microns. Past that, you get into radio, you get into microwaves. Below that, you get into what your UV, even below UV, gamma rays. So those act differently, cannot use optics to manipulate that kind of light. So that's outside the realm. Broadly, optics is between classical and modern optics. My job is 90% geometric optics, which falls within classical optics. Right here, we have a ray trace of a mid-wave lens, I believe, actually. And this is an example of geometric optics. You have lines going in. They're manipulated by the lenses through Snell's law, and they produce an image later on. You'll notice a lot of lens groups. Those correct aberrations, achieve certain, you don't have to worry about that, but this is an example of how complicated geometric optics are, even though there's wave optics, which falls under physical optics, and quantum optics, which is like cameras, sensors, and lasers. So that's about optics. All right, we know what optics are. What's infrared light? Infrared light behaves very similar to visible and UV. If you can do visible optics, you can do UV or infrared. The main difference is how it interacts with media, your materials you're using. Obviously, we're going to get to this on the next slide, but infrared is all around us. We glow in the infrared. But design concerns with infrared really only begin past 2.5 because it's so similar to visible light. People often hear infrared and they think about heat, which isn't exactly wrong, but infrared light is not heat. All light can produce that effect. It's just that we happen to live in a world which is around 300 Kelvin or whatever, and that means our bodies and the things around us emit in the IR, specifically the long wave and mid-wave IR. So we often think about heat as infrared because that's how we can imagine the heat around us, right? So infrared optics are used in thermal imaging systems, but it is important to remember that infrared is not heat. And here's more about thermal radiation, because it really gives impetus to why we do thermal optics and IR optics. So here we have a blackbody curve with a few different temperatures. Even if you're unfamiliar with the blackbody curve, I promise you've experienced it. When something gets hot, it glows. That's what the blackbody curve shows us. Importantly, as it gets hotter, it glows in shorter wavelengths, which is why you have an iron poker in the fire. It won't glow, and then it starts glowing that dull red and then orange. That's the blackbody curve, right? Like I said, everything around us, everything glows. We just happen to live in a world that glows around infrared, way down here, past that 3,000 Kelvin curve. So now, everything can be described by a black body. Everything glows like a black body. But in reality, there's physical effects, absorption, emission, emissivity, things that make us not black bodies. And what's interesting is that we can compare the curve of the theory to what we're actually seeing, and that tells us something about what we're looking at. It tells us what's being absorbed. It tells us how reflective the object is. Because so much stuff around us glows in the IR, that's actually pretty useful for learning about the world around us. Thermal radiation is also a big reason why IR astronomy is really important. Not everything is all about thermal and IR astronomy, but we'll get there. Since I'm an optical engineer, I thought I'd talk a little bit about the design considerations, a little bit about the difference between like visible and long wave, how those optics differ. Near IR is basically visible light. If you have a camera, it can take a near IR photo. You might have to pop a filter off or adjust your lens. IR will focus further than vis because of chromatic aberrations, but past that, there's no difference between vis and near IR design. Then you start getting to the SWIR and midwave when materials start mattering. On this lens, this is a midwave lens. You can kind of see that the front lens there is a little purple, maybe pink. A lot of lenses that's green. I'm colorblind. So a lot of lenses have different colors of material, and you may look at that and go, oh, that doesn't, you can't see through that, but that's an example of how IR light can pass through some things that vis light can't, and vice versa. A lens that you might use on your camera would be completely opaque to IR. So we have to use different materials. When we get to the midwave and long wave, the actual design of the lens can matter a lot because the lenses themselves have temperature and they emit in the IR. So you have to be really careful that you're not imaging your own lenses. And that really drives a lot of design considerations. And then there's different sensor materials. You get some pretty cool, like indium antimony is used for midwave. You get some pretty obscure kind of materials going. So let's get into the actual astronomy. IR astronomy is actually a newer field of astronomy. It wasn't really considered as useful until the 60s. And then it was actually spurred on by the use of radio astronomy, and everyone kind of got excited about different wavelengths and what we can learn. And then IR astronomy really took off. The first telescope designed for IR was launched in 1983. A lot of the science we do in IR is driven by satellites, and that's because our atmosphere has a big absorption band right in the IR from water, and then a few other ones from CO2, which, by the way, is also why CO2 is, it's a greenhouse gas, of course, but it's dangerous because it absorbs IR readily, and that's all around us. Obviously, the biggest news in IR astronomy recently was JWST, James Webb. Everyone heard about James Webb, which was really cool. But it's out there performing a lot of new science, a lot of cool pictures. Next up is the Roman Space Telescope, which was actually a NRO telescope, reconnaissance office. So it was a spy telescope from the early 2000s, which was bought in 2012 for use by NASA, and they kind of co-opted it and made it into their mission set. And it's going to be one of the most advanced IR telescopes ever. And I think it's funny that, a telescope designed 27 years ago for spying is now going to be a revolutionary science asset. So that's kind of interesting. IR is good for astronomy because we have stuff out there like dust, cold nebulas, galaxies which are moving away from us, star formation, which happens in a lot of dust and nebula, and exoplanets, which can be often obscured by their star and the previous dust and nebula. So let's start with those nebulas. This is a really cool comparison. Everyone's seen this photo. It's the Pillars of Creation. On the left was taken by Hubble. On the right was taken by James Webb. You can just see how much more space behind the nebula you can actually see. The IR really penetrates that dust, which is also why we use it here on Earth for tracking systems and observation systems, is you can just cut through the haze and the dust and all that shit out there, and you can just see what you're actually trying to look at. And in this example, you can see actually stars in the dust that you couldn't see on the left. And those stars are, the Pillars of Creation are called that because it's a very active star-forming region. So better IR astronomy has allowed us to better study areas like this where we have active star-forming areas. Also, cold nebulas, which you can't necessarily see invisible because they're cold, show up, they glow in IR. So, they just light up like a light bulb out there, and you can learn a lot more about what is actually out there, the dust and the gas, which makes up the vast majority of our galaxy and the universe. Planetary science. This is a cool photo, too. This is of Jupiter. From this photo, they actually learn more about the atmospherics on Jupiter. They learn more about those strong bands of winds going across the planet. We can also use it to IR astronomy to learn not only about our own planets in our solar system, but exoplanets. Exoplanets are often hidden by their star. Their stars emit strongly, remember black body radiation, emit strongly invisible, but less strongly in IR. So when we look at these systems with IR instruments, we can see the details of the planets orbiting them a little better. And we've discovered a lot of exoplanets with JWST and its improved resolution and its IR equipment. And then redshifted galaxies. So a lot of you might know that the universe is expanding. This expansion actually pushes the light being emitted by galaxies into further and further red wavelengths, lower energy wavelengths. That means a lot of our universe around us we can't actually see in the visible wavelength. It's why the sky is dark at night. If it weren't for redshifting, the sky would light up and you'd be able to see everything, from the Big Bang, all the light. But no, light is redshifted, and that means a lot of the universe is hidden to us. Using IR astronomy and then radio astronomy and further wavelengths, we can look further and further back in time. James Webb was really exciting to cosmologists because of this. We can now see further images of galaxies than we've ever been able to see before. James Webb has taken a photo of the oldest galaxy we've ever discovered already. This is a photo of the James Webb Deep Field recreating a Hubble photo. This photo is cool because you can see gravitational lensing. You can see some of those galaxies curving around a center spot. That's cool. That's optics caused by curvature of space-time instead of materials. That's relativistic optics past even quantum. It's pretty neat. So I promised to talk about where else IR optics is used in my title. So we'll just go through some of these. I don't know a lot about these things because they're not in my field, but one of my more favorite applications of IR optics is in art restoration. You can actually see underdrawings because, like I talked about, just because it's visible in the visible wavelengths doesn't mean you can see it in IR. So IR just punctures right through the paint, and you can see the underdrawings, which are often done in carbon black and pencil. And that just absorbs IR really well. So that's a photo of the Mona Lisa with an IR instrument. Agriculture, it can see through the skins of fruits and vegetables. This is a midway photo, hard to see, but this is a midway photo of an apple, and the bruises on the apple kind of show up better. You can choose how, to someone selling apples, you can choose which ones to sell beforehand by looking at your fruits and vegetables using IR. Point-to-point communication, we do this at my company, not in my division, but laser communication can be done with IR. You can put two telescopes far apart from each other and talk to each other point to point without concerns of anyone else listening, as it happens a lot faster than other communications. It's a developing technology, and it's pretty cool. Weather, cloud formations have different temperatures. You can look at those clouds from space and tell what kinds of clouds they are, what the weather system is doing. So that's an interesting use. Transportation, all of our cars can maintain a lane. That's probably done invisible, actually, but a lot of the self-driving features, like how far to stay away from the car in front, that's using IR LiDARs with cameras, probably visible cameras. And of course, phones and technology. All the biometrics, face scanning is done with IR. So that's just scratches the surface of how many fields and what we do with IR. But I hope you enjoyed my talk. Do you guys have any questions? Yes. The question was, are the colors in these IR photographs I'm showing you coming from the photos themselves, or what's going on there? These have all been false colored. When you take an IR photo, we have a lot of SWIR cameras around the office. They appear black and white. Some mid-wave, long-wave, we color in what we call red hot, cold blue, which gives you that kind of thermal picture everyone's familiar with. But something like this has actually been colored with the colors representing what material you're looking at. So blue in astronomy is often oxygen, red is often hydrogen, yellow might be something else. So that gives you a scientific idea of what you're looking at using colors we're used to, even though it's a IR photograph. Yes? So optics, the question is, do spies care about the same things as astrophysicists? I'm assuming that means towards the design of the scopes themselves. Optics is optics, whether you're looking at something small on Earth or looking at something small, light years away in the galaxy or in the universe. Those designs are very, very similar. Roman has probably been in some way changed. I'm sure its original design and what it was designed to do is super classified, and NASA's changed it in ways they won't talk about. But yeah, no, a telescope's a telescope. You can use a spy telescope and point it up, and it'll perform exactly the same. Yes? Yeah. Yeah. Yeah, so the question was about HOV lanes and how they know how many occupants you have in your car. I don't know if that uses IR or not. It might. Like I said, a lot of IR windows are actually completely translucent to IR, so you can't actually see through windows. So I wouldn't be surprised if they're using visible wavelengths for HOV lanes. Yes? Okay. Okay, so it's just a scope. Okay, so it was a comment, and the comment was he knows some people who worked on Roman, and he was saying that it was given without any instrumentation. So that is probably how NRO hid their secrets from NASA and the rest of us. Any other questions? Oh yeah.
Some car proximities use IR?
Yeah, car proximities will often use laser ranging to figure out how close the car in front of you is. That's done in IR. It's more 1550 nanometers is actually a safer for your eye. It's considered eye safe because it's absorbed before it hits your retina. So we'll often use 1550 for eye safe applications like laser ranging when you might be sending a laser out and you don't know it's necessarily going to hit.
It's not looking for IR, it's sending it out.
Yeah, yeah.
Temperature doesn't matter if you're in Canada.
Exactly, exactly. So that's a distinction I tried to make, is that temperature and IR are related, but only in so much as all light is related to temperature. So in that application with cars, you send out a pulse, and it comes back, and you can measure using the speed of light how far away that car is. Yes? Oh yeah, that's a good question. The question was about lens materials for IR optics. Like I said, near IR is going to be your standard glasses. I could list off some glass. You guys wouldn't know what I was talking about, but just standard crown and flint glasses. When you get up to midwave, you start getting like silicon optics. They're actually ground silicon, pure elemental silicon. Midwave is super translucent, or silicon super translucent to the midwave. Long wave materials are going to be similar to your midwave materials. I don't know if there's any specific long wave materials. There are materials which are translucent from, or transparent from UV all the way up to long wave. Like sapphire is a super, super clear material. So we use a lot of sapphire windows, especially for hyperspectral applications, which might be looking from the visible to the midwave. So, any other questions? Thank you, everyone.
Give Connor a round of applause. Thank you so much.